Hello and welcome everyone. So today we will learn on pitting and passivity. Let's go. Passivity, a condition of corrosion resistance due to formation of thin surface films under oxidizing conditions with high anodic polarization. The formation of the metal oxide can be a purely chemical reaction or an electrochemical reaction. In simpler words, it means that the material is less prone to corrosion because it develops thin protective layers on its surface. This happens when the material is exposed to conditions with oxygen, and there's a specific type of electrical influence that strengthens its resistance against deterioration. If we are comparing these two steels, we can find the difference that stainless steel gets a protective shield which is passive film from the chromium it contains, making it resistant to corrosion. While carbon steel, without the protective effects of chromium, it reacts with oxygen and moisture, forming rust, which weakens and corrodes the steel over time. Passivation. It is a process used to remove iron from the surface of corrosion-resistant steel parts so more uniform formation of a passive surface is obtained and enhanced corrosion resistance. Next, the discussion is proceeding with passivating films mechanism. There are two mechanisms which are 1. Precipitation in passivating film. When specific elements or compounds in the film react with each other, they create solid particles that settle within the film. These solid particles contribute to the structure of the passivating film, making it more stable and protective. It creates thick layers on the metal surface. These layers have some tiny openings which known as porosity, a specific structure, and don't conduct electricity well. This process is known as passivation. 2. Anodic reaction in passivating films. This reaction involves the loss of electrons from the metal surface. This loss of electrons is part of what contributes to the formation and maintenance of the protective passivating film. This method results in passivity. It mainly influences transition metals like Fe, crossing, Mo, W, Zr, and alloys such as stainless steels. Example: stainless steels, because of their chromium content, develop a protective layer mostly made of chromium oxide. It broadens the range where these steels can form protective films. Passive films generally consist of two layers: an inner film composed of a barrier, oxide layer and an outer layer composed of a precipitated phase, which may react with cations or anions from the solution. There are a few conditions that cause a metal surface to become passive or lose its passivity. 1. Aggressive anions. Adsorption of aggressive anions can react with metal ions and cause chemical dissolution, and more aggressive anions cause the breakdown of the passive layer and pitting initiation. 2. Temperature. Temperature affects the speed of chemical reactions. Higher temperatures can accelerate the processes that contribute to passivity breakdown. 3. pH. Extreme pH levels can weaken the protective film, compromising its ability to shield the metal. A low concentration of aggressive ions avoids interfering with the metal passivity mechanism. However, at high concentrations, the destruction of passivity will happen. Lastly, there are different mechanisms for passivity breakdown to happen, leading to pitting and localized corrosion in passive metals. Among them, the penetration and film breaking mechanisms are two important mechanisms. 1. Penetration mechanism. This mechanism includes the transmission of aggressive anions to the metal surface through the passive film. The incorporation of aggressive anions affects the film surface and increases the ionic conductivities along penetration paths. Ion penetration of oxide films was capable through an ion exchange process or through cation vacancies. The oxide layers on the metal surface contain defects and are porous in nature. 2. Film breaking. Film breaking involves the rupture or failure of the protective film itself on the metal surface. When the film breaks, it exposes the underlying metal to the surrounding environment, making it vulnerable to corrosion.
Stainless steel is composed of iron, carbon, and chromium. To be classified as stainless steel, the material has to contain at least 10.5% chromium. The chromium oxide layer that appears on the surface of stainless steel protects against the harmful effects of rust and other aggressions. Nevertheless, thermal treatments such as welding, mechanical abrasion, galvanic corrosion, and strong acids can damage this protective layer. Fortunately, by combining oxygen and chromium, this protective layer can reform. This process is called passivation.
Chlorides attack the stainless steel surface, dissolving the chromium oxide passive film, producing chromium chloride salt and hypochlorous acid, or hypochlorite ClO. Hypochlorite, the active ingredient in bleach, attacks the base metal, deepening the pit, forming
metal are corroded from specific areas on the surface, forming craters or pits. In severe cases, this corrosion can lead to complete perforation of pipes or vessel walls. Pitting can happen on a metal surface when it's exposed to stagnant or slow-moving liquids. It's important to note that pitting can be the initial stage for other types of corrosion. Pitting corrosion can take different shapes, depending on the material and grain direction. Passive metals like stainless steel and aluminum are often affected, but almost any corrosion-susceptible material can face this issue. Trough pitting, appearing hemispherical or cup-shaped, occur when the protective film is compromised, forming narrow and deep troughs that can quickly penetrate material thickness. Vertical grain attack trough pitting corrosion. Elliptical trough pitting corrosion. Narrow, deep trough pitting corrosion. Shallow, wide trough pitting corrosion. Sideway pitting, covered in a rust layer, results from horizontal grain attack and can swiftly penetrate metal. Detecting sideway pitting is challenging, as the metal surface may seem unaffected, giving the impression of minor damage with only a few small rust spots. Horizontal grain attack sideway pitting corrosion. Subsurface sideway pitting corrosion. Undercutting sideway pitting corrosion. Pitting corrosion in copper can manifest in 3 types based on water conditions. Type 1 pitting occurs in hard or moderately hard waters with a pH between 7 and 7.8, especially in cold water. Results in deep and narrow pits pose a risk of pipe failure. Type 2 pitting happens in certain soft waters with a pH below 7.2. Rare in temperatures below 60, pits are narrower than Type I but can still lead to pipe failure. Type 3 pitting takes place in cold soft waters with a pH above 8.0, results in more widespread and shallow pits, leading to issues like blue water, byproduct releases, or pipe blockage. Pitting goes through 4 stages: initiation, propagation, termination, and reinitiation. It starts with a local cell causing the pit to form, either due to an abnormal anodic site or an abnormal cathodic site. This is the starting point. A pit forms because of an abnormal spot on the metal surface, acting as either an anode or a cathode. Post-examination can reveal the initial point of attack. The corrosion rate increases as the environment around the pit becomes more acidic or alkaline. A pit may stop growing if internal resistance increases, often due to corrosion product buildup. The pit can stop growing if it dries out, but re-wetting can restart the corrosion process. The movement of the liquid over the metal surface can prevent or reduce pitting. In April 1992, over 200 people died, and 1,000 buildings were damaged in sewer explosions in Guadalajara, Mexico. The blasts were caused by a gas leak, ignored by the government and National Oil Company. The tragic explosions unfolded as leaking gasoline from a corroded pipeline seeped into the city's underground sewer system. The presence of different metals in the pipes led to corrosion, creating gaps for gasoline to escape. The intricate network of underground pipes allowed the gasoline to spread. Dangerous fumes built up in the sewer, intensified by hot weather. A spark, possibly from maintenance work, ignited the trapped fumes, triggering a series of explosions that ravaged the city streets over several hours. Days before, residents noticed a foul smell and experienced discomfort, but authorities dismissed complaints. Starting around 10:30 a.m., explosions created a nearly 2 kilometers jagged trench, contiguous with the city sewer system. Open holes, at least 6 meters deep and 3 meters across, formed. Larger 50 meters diameter craters were evident in multiple locations, with vehicles buried or toppling into them. develop pitting corrosion when exposed to aggressive substances like acidic foods, salt water, or harsh cleaning chemicals. Pipes made of metal, such as copper or iron, in residential or commercial plumbing systems, can be susceptible to pitting corrosion. Factors like low pH water, oxygen concentration, or chemical imbalances can initiate pitting within the pipes. Boats made of metal, such as aluminum or steel, operating in marine environments, are prone to pitting corrosion due to constant exposure to salt water, wave action, and galvanic effects. The following countermeasures can be adopted to prevent pitting corrosion. Selection of materials that are known to possess a level of resistance towards the given environment, exhibiting a level of control over the environment, including its pH, temperature, and the concentration of chloride ions in it. Employing